Welcome to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover the kernel and the range of a linear transformation. So let's start with the kernel of a linear transformation. So we have a transformation that takes vector space V to vector space W. Then the set of all V in the domain space that satisfy this equation, T of V is equal to the zero vector, is denoted by the kernel of T. So what we can say is that the kernel of T is all V in the domain space such that T of V is equal to 0. So if you wanted to call back to like maybe an algebra class, we're kind of talking about like the x-intercepts of a function, because the x-intercepts are where that function maps to, 0. So we're doing this in, much larger spaces. So what we have is if V is our vector space and we have W being our codomain, what I know is that since W is a vector space, there's a 0 in there. And the kernel of this vector space is going to be a subspace of this vector space, but that subspace satisfies, all the elements V. So what I have is I have a whole bunch of vectors in here. So every single vector in this subspace will map to the 0 vector. And that's what we mean by this. Every single V in here will map to 0. So let's have a look at a couple of them. Now, it doesn't have to be a space bigger than the trivial space, but sometimes it could be. So let's start out with this linear transformation. So we're going to go from 3 rows, 2 columns to matrices of 2 rows, 3 columns simply by the transpose. And I'm trying to find the kernel of this. Now, the kernel is trivial because I'm really asking T of what I'm going to have is, I have 3 by 2, so this is going to be 3 rows, 2 columns. And what I want to do is when I set it through this transformation, which is nothing more than the transpose of this particular matrix, I'm just kind of putting empty dots in here. What we know is what's going to happen is it's just going to simply be, this first column becomes this first row, and this column becomes this row as well. Now what I'm asking for is I want T of this thing to be equal to the 0 vector. Well, the 0 vector in its codomain is going to have to be 0, 0, 0, 0, 0, 0. And remember that this first row came from this first column, so this first column would have to be zeros. And similar, this would have to be zeros as well. And then backtracking, this is the input, this is what I was plugging in. So let's kind of work through that. So T of this input says I'm just doing the transpose of its input. Well, the transpose of an input is going to be this. So the only way to get this 0 vector back would I'd have to use the 0 vector of this thing. So in this case, the kernel of this transformation is nothing more than this set right here. 0, 0, 0, 0, 0, 0, 0, 0, right here. Simply that single vector. Let's look at a little more geometric, and we'll work in the Euclidean spaces because they're super easy to draw. So this transformation, T of x comma y, the first component is going to be x plus 2y, the second component is going to be negative x plus y. So really what I'm trying to do is I'm trying to solve T of x comma y is equal to 0 comma 0. So in order to do that, I know that T of xy is equal to this, so I'm going to have x plus 2y, negative x plus y is equal to 0 comma 0. So then, first component has to equal the first component, so x plus 2y would have to equal 0, and then negative x plus y would have to equal 0. And we can solve this through systems, or we can, this is a linear algebra class, so we've worked a lot of matrix work, so this would be 1, 2, 0, negative 1, 1, 0. And what this will reduce to, or row reduce down to, row reduce echelon form, that matrix is going to be equal to 1, 0, 0, 1, and these will be zeros. So what this says is this first line says x is equal to 0, and the second line says y is equal to 0, or 1x plus 0y is equal to 0, so x equals 0, and 0x plus 1y means y is equal to 0. So what we get again is that the kernel of this transformation, again, is just simply the 0 vector. So if I was going to draw this from R2 to R2 as far as transformation-wise goes, what I know is I'm going from, R2 to R2 because that's what it says. So I'm taking every vector in here and spit out a vector in here. Well, the only vector that works would be this vector right here will map to, the 0 vector right here. This is the only mapping. So in this case, it's the trivial one, that the kernel, this is the only vector that maps to 0. Now, one that's not trivial. If I want to do this, what I know, again, I'm trying to solve, t of x comma y is equal to the 0 vector, so 0 comma 0, the 0 vector that's codomain. So t of x, y is this function rule, or transformation rule. So this is x plus 2y, this is negative 2x minus 6y, is going to equal to 0 comma 0. So setting this up as a system, and rewriting this as a matrix to make our systems easier, we have 1, 2, 0, negative 2, negative 6, 0. And I'm sure you might have recognized this already, that this, this second row is nothing more than negative 2 times the first row. So when we row reduce echelon form this, in order to solve its system, it's going to be 1, 2, 0, and this would be 0, 0, 0. Which means we get infinite solutions. So the first row says x plus 2y is equal to 0. So I have x plus 2y is equal to 0, which means I have to put this in parametric. So x is equal to negative 2y, let y equal t. So then our solution space, our x comma y, is, well, x is negative 2y, which is negative 2t, and then y is just t. And what we know is that this defines a subspace. So the kernel of t is going to be, well, this defines a basis. So negative 2 comma 1 t. And the basis of this subspace is going to be this vector. And we'll explain what this means in a second here. So this is negative 2 comma 1. That's the basis. So let's explain what this is, because we've been through a lot of linear algebra now. And what we know is that this is a basis with one parameter, which really means that this is linear. And you can see it here, this is linear, that x plus 2y equals 0 is nothing more than a line in R2, or x is equal to negative 2y. So, this thing is nothing more than, you go over 2, up 1, and that's the first vector right there. And since it's all linear combinations of that vector with that one parameter, it's really going to be this line right here. So any vector on this line, any vector on that line, I'm just going to do it this way, will map to the 0 vector in the codomain. So moreover, what we have is the kernel of t. So really what we have is that the kernel of t is a subspace of V. And we proved it. This is a basis of a subspace, and this is a vector in V. This is a basis of a subspace. It just happens to be the trivial. And then this also is, the basis of a subspace, which happens to be the trivial a subspace for, that vector space right there. Now, it could be in the entire space as well. So, you could get the identity, you could get a line, you could get the entire thing. Because if we're talking about subspaces. Now, the way you get the entire thing is you'd have to say t of x comma y is always equal to 0. So that could happen. The kernel of t is a subspace of V. So our example is going to be find the basis of the kernel of t. So our transformation is going to go from R5 to R4, and it's going to be defined through matrix multiplication. In our next video I'm going to define all linear transformations as matrix multiplication. So this can be done with every linear transformations, and we shall prove it. So x is an element in R5, so we're going to write this vector x as x1, x2 all the way up to x5. So this is going to be our matrix multiplication. So really what we have here is t of x comma 1, 2, 3, 4, 5 is going to be equal to this matrix multiplication 1, 2, 0, 1, negative 1, 2, 1, 3, 1, 0, negative 1, 0, minus 2, 0, 1, and then finally 0, 0, 0, 2, 8 multiplied by x1, x2, x3, x4, x5. And we could see that this would look much like a regular linear transformation if I was to do the matrix multiplication. So, its first component would be 1 times x1, 2 times x2, 1 times x2, 2 times x2. So this would be x1 plus 2x2 plus 0x3 plus x4 minus x5. The second component would be 2 times x1, 1 times x2, 3 times 1 times x4, and so on. So this is going to be 2x2 plus, x1 plus x2 plus 3x3 plus x4 plus 0x5, and then I'm going to say and so on. So you can see that you can write this as a linear transformation that we're accustomed to. So this truly is a linear transformation. Now, if I want to find the kernel of this linear transformation, I'm trying to solve this. So in order to find the kernel of t, we must solve t of x is equal to 0. Now remember that t of x is equal to a times x, so we're really just saying that a times x is equal to 0, which is something we've done in a previous video or lesson for linear algebra. This is nothing more than the null space of this matrix. So really the kernel of a transformation is the null space of that matrix multiplication. So in order to solve this, we're going to join this with 0. So remember that I guess I could draw it the wrong way, then we'll join. So what we're doing is we're taking this, multiplying by x1, x2, x3, x4, x5, and then this is supposed to be equal to the 0 vector. Remember, it's got to be the 0 vector in its domain space, so it's codomain space. So I need it to map to here. Okay, now I can rewrite this by adjoining these two matrices, so this adjoined with this. So I'm going to have 1, 2, 0, 1, negative 1, 2, 1, 3, 1, 0. Adjoin with the 0 vector. So what I mean by that, to be clear, what I mean by that is remember that this is supposed to be equal to this 0 vector here, which is in the codomain. So these zeros are going to be these zeros. I'm pretty sure we're accustomed, we're used to this by now. Okay, so what I'm going to do is I'm going to row reduce echelon form this, and what we're going to get is we're going to get 1, 0, 2, negative 1, 0, 0, 1, negative 1. I'm missing this. Okay. Now again, these zeros over here are these orange zeros. Well, what does this actually say? Well, remember that that this is nothing more than a system of equations, and this says x1 plus 0x2 plus 2x3 plus 0x4 minus x5 is equal to 0. So let's write that. So this says x1 plus 2x3 minus x5 is equal to that 0. And then the next line says x2 minus x3 minus 2x5 is equal to 0. And then the last line, well, the last line says the zeros, but the third line says x4 plus 4x5 is equal to 0. which we know means an infinite set of solutions. So either, it's not going to be the trivial solution, which is just a zero vector. You might get a line, you might get a plane. Who knows? It's going to be some subspace in here. So what I'm going to do is I'm going to solve these. I can see that they share an x5, so I'm definitely sending x5 over. And I'm going to solve this one for x1 and x1 here, x2 here. So x1 is going to be equal to minus 2x3 plus x5. X2 is going to be equal to x3 minus 2x5 plus 2x5. And x4 is going to be equal to minus 4x5. So we're going to parameterize this. I can see that this is clearly going to be a plane now because I have two parameters. I have x3 and x5. So let x3 equal s and x5 equal t. So now remember that I'm trying to find this so that we spit out 0. So let's set this up as our input space or a domain space. So x1, x2, x3, x4, x5 is our input. And that's going to be equal to this parameterized. Well, x1 is minus 2s plus t. So minus 2s plus t. X2 is going to be s plus 2t. X3 is just s. X4 is just t. And x5 is minus 4t. So this is a linear combination of vertical matrices. So what I mean by that is, it's going to be one matrix times the parameter plus the other matrix times the parameter. Remember this, a linear combination. It was like C1V1 plus C2V2. Well, this will be C1V1 plus C2V2. So these are the vectors or the basis of the subspace. So this is going to be negative 2, 1, 1, 0, 0. As you can see, all the coefficients of s and all the coefficients of t are going to be 1, 2, 0, 1, minus 4. For some reason, I think I have that backwards. What do we have here? No, I'm good. This is fine. Okay, so x4. I do have it backwards. X4 is minus 5xt. So x4 is going to be, x4 is right here, minus 4x5. So this would be minus 4x5 is t. And then x5 is just t. So I do have those things backwards. So this should be a minus 4 and this should be a 1. So that means, let's write the kernel of t as a subspace. Now remember that this really is the notation that we take, not really this notation. So these bases I'm going to write as, elements inside of, V. So this is going to be, the kernel is minus 2, 1, 1, 0, 0, and then 1, 2, 0, minus 4, and 1. So that is the kernel of this subspace. Alright, sorry to make the video so long, but we're going to do the range because it lines up so nice. And that'll do it for us. Okay, so I should discuss this. Now what we know is that the kernel of T is going to be a subspace of our vector space V. So in this case what I have is I have a two-dimensional subspace, so that the kernel of T happens to be, it's a two-dimensional subspace, but this is a two-dimensional subspace in this domain space, which is R5. So this is a plane in R5. So that thing right here is this kernel of T. And what we know is that this is going to map to the zero vector in its codomain. So this is going to map to this thing's zero vector. Sorry, not V, but zero vector. So everything in here is going to map to the zero vector. Now, the next thing I want to talk about is the range of a transformation, and the range is something a little bit different. What we're asking about for the range is, let's go back to our vector space V and then our vector space W right here. Well, what is the range? Well, not every vector in this thing right here, not every vector is going to map to all of W. Now, it could, but it doesn't have to. So sometimes what's going to happen here is V is going to map to a subspace in W. So all vectors in here will map just to this inside of this. So in this case, the yellow being the subspace of W, and the subspace of W is going to be the range of V. And the way we're going to find the range of V, which is a subspace of W, is using this theorem. So the range of T is equal to the column space of A. So we can actually do that with this previous example. We have a lot of the work here. So what I'm going to do is, instead of finding the basis of the kernel of T, we're going to find the basis of the range of T. Now the range of T is nothing more than the column space of this matrix here, and we've done some row reduction. So instead of finding the kernel, I don't have to solve this. What I need to do is I need to find the column space of this matrix. And one way to find the column space of the matrix is to simply row reduce the matrix and then find its linearly independent columns. So what I know here is that I can row reduce this matrix, and of course it's going to row reduce to the same coefficient matrix that we had before when finding our kernel. So in order to find the basis of the range, what I can now do is I can look at the linearly independent vectors, or the linearly independent column vectors, which are going to be here, here, and here. So what I have is column 1, column 2, and column 4. Which means it's actually going to map back to these things being linearly independent. Column 1, column 2, and column 4. Which means the range of the transformation is equal to the column space of A, which is going to be these things as a basis. So this is going to be a basis of 1, 2, negative 1, 0. This is going to be 2, 1, 0, 0. And finally 1, 1, 0, 2. Now remember that the column space, this is a subspace of this, of R4, of the codomain. So it's going to be the subspace of the outputs. And we can see that this is R4 vectors. It's not all of R4. This is a three-dimensional subspace of R4. And what is a neat theorem that we knew before is that we can say that the dimension of the null space, which is also equal to the nullity, so the nullity, which is the dimension of the null space, or the dimension of the kernel, was equal to 2. What we know is that the rank, which is the dimension of the column space, is equal to 3. And this is an M by N matrix, so this is a 4 by 5 matrix. So we can see that 5 is what I'm actually looking at here, is that 2 plus 3 is equal to 5. So it's kind of neat that this has dimension 2, and that means the rest of it would have to spit out to a dimension 3, because all of this is 5-dimensional. So if you like the content, please subscribe.